Me too. Friendly reminder that your first exam will be next Wednesday. As we discussed in class last time, some of the details. Anybody think of any other questions or concerns you might have had about it? Monday we'll review. Today I intend to finish chapter 5 on Newton's third law. I have some review questions on it planned that I'll ask Monday. Clickers. And then the way I do reviews is, well, it's review, but they're better. What I'm getting at is this weekend, look at your past homework. Look at the pre-lectures, the stuff in the book and the past lectures. What are you still confused about? What doesn't make sense? What are your questions? Anything. Because that would be the time for you to ask them. And we can focus on what you're specifically wanting to know instead of me shooting from the hip. Oh yeah, remember we did this and we did this, but I'll do that until you guys ask questions. But that Monday's all review, nothing new. Actually, today's not really much new either. We're just going to do more with Newton's third law to solidify it. But we started the main concept last time. Homework is due Sunday. Homework on chapters 4 and 5 will be due Sunday. Okay. Clickers. If you have purchased a license and a clicker, how should I say this? I know there's a couple of you that aren't getting one, period. You just decided, and I can tell that. But if you've gotten one, I'm getting everybody's responses except these that have come and done any response at all. There's several people that I can't tell if they just haven't come to class, but I've got nothing from them. But I am getting responses from these 6 individuals, but I don't know who they are because they're still unassigned because you haven't gone through the procedure correctly or something. So if these are one of you, let me know. Now, after class, email me or something. At least then maybe I can figure out what's going on if you haven't. If it's responseware, that would be shown in an email he sent you or in your Turning account. And if it's a actual clicker, the device ID number should be right on the back or in a menu setting. Again, if that's one of you, I have your responses. I just don't know it's you yet, so contact me. Okay. What's Newton's third law? Oh, that's music to my ears. Lots of you responding, and it sounded correct. For every action, there's an equal and opposite reaction. All forces come in pairs. You can't be interacted on without interacting with the something that interacted upon you. See, we don't say it like that because it doesn't sound as good, does it? But that's what it means. So let's do a demonstration to pound this in. I need 2 volunteers. We're going to sit on these rolly carts. Any takers? 1? Yeah. Okay, Jordan. All right. We're going to have you sit on here. How about Jordan, you come on this side. You can sit here. Crisscross applesauce as close to the edge as possible, facing each other. All right. Who wants to be the wall? Who's feeling like a wall?
I don't care.
Okay, you be the wall. You're going to put your hands up like this. And your point is don't move. Don't put you're rigid. All right. You put your hands on her and I want you to push on her. Okay, we'll try it again. Come back together. This time don't push. Okay. I mean you push, but you're not supposed to push. You're just a wall. You're rigid. Okay, push. Okay. All right. This time you're the wall. You're the wall. Don't move, okay? Now push on him hard. What do you think's going on? Hey, you both have wheels.
Am I doing it wrong?
No, this is exactly how we're supposed to work. I'm just hamming it up. Why do they both move?
Because for every action.
What was that? Yeah, exactly. Even though, when you're the wall, when you push on her, she pushes back on you, whether she intends to or not. In order to be rigid, you have to push back on him, and vice versa. And how do the forces compare? They're exactly the same. That's Newton's third law. So explain what you saw. Who moved more? I thought I just said it was the same force. Yeah, the force is the same, but because she has less mass, no offense, she accelerated more. She had less inertia. Let's try it another way. All right, fill this. We'll start together again. Let him feel it. It's used to no surprises. All right, we're going to toss it back and forth as fast as you can. Go. Yeah, we'll probably stop there. What happened? Yeah, they still moved. Okay, when he pushes it, what's the action-reaction pair? He pushes on the ball. The ball pushes back on him, so he recoils. All right, it comes over. What does she do to stop the ball? She pushes on it. She exerts a force to stop it. So she pushes on the ball to stop the ball. What's the ball do? Pushes on her, so she recoils. And then vice versa when she tosses it. And again, this force is the same, but because she has less mass, she moves more than the same force of push over here. It even works. We'll start far apart this time. All right, you just hold on to it, and Jordan will pull. And they both move. Thank you very much. I appreciate it. Couldn't do that by myself. So it even works with the pull. She pulls on the rope. Well, the rope pulls on her. At the same time, it's transmitted through the rope through tension. Tension's a force. And it pulls on him. What's your name? Carl. I feel guilty. I know her name, but I keep... Thank you, Carl. That's Newton's third law. Questions? Comments? Peanut gallery. So the trick here, there's no trick, but this is one where your intuition fails you a little. You're tooling down the highway and a bug splatters on your windshield. I grew up in Kansas. We had lightning bugs. And every once in a while at night, it would be glowing. They're ones where they have a chemical in their hiney and it glows. They're fun. And while it was lit up, it's when it hit my windshield. And it would leave like this glowing streak along the windshield. So, messy, but it was pretty. How do I want to ask this? Yeah. Where was the force greater? On the bug or on the windshield? You're getting it. In physics class, you're getting it. It seems obvious right now, doesn't it? Before this class, I bet 90% of you would have said, oh, the bug felt more force. Am I right, if you're being honest? No, the force was exactly the same between the two. Who could handle more force? The car. So it didn't give, but it still felt that force. The bug couldn't because it had less mass, less resistance to changing its motion, inertia. Yeah?
So is it the acceleration that kills it?
It's the stopping, yeah. The acceleration, the change in velocity from something to zero, or, well, yeah, it's stopping him, yeah. Yeah. We're going to cover that too. We'll get into collisions. It involves momentum and impulse and the forces there and the times involved. Exactly. It couldn't handle it. Okay. Oh, I'll use this. I meant to bring something else. This one gets some folks too. Let's use this same 10-pound medicine ball. All right, I'm going to try to hit it the same as I hit the washcloth. Oh yeah. If I try to use the same force and hit this. Oh yeah. So again, I'm trying to be consistent. Versus, uh-oh. All right. Which one felt more force? All right. If my force of hand on ball, force of ball on hand, how do they compare? Excellent. That's correct. Force of hand on rag, force of rag back on hand. Good. Correct. Force on rag versus force on ball. I'm trying to do the exact same thing. They are not the same. This can't handle it. It can't push back as hard because it's not as strong. Let's take it to the extreme. Push the wall. I'm not going to do that. I will when we get to momentum and impulse, but not right now. If I hit that, you know it's going to hurt my hand more. My hand can't take it. The wall can handle it. Now picture it as a pillow. If you punch a pillow, what does the pillow do? Yeah, it gives. Take it to the other extreme. Can I borrow you? I'm not hitting you. Don't worry. Or you can do it to me. Here we go. Pretend like you're hitting my face. Slow motion. Okay, do it again. Look, there's no force between his hand and my head. Do it again. That's kind of fun. If I'm moving away, then he can't push against me. Thank you. That's what happens here. It can only stay put based off its mass and inertia and structural integrity up to a certain force. Beyond that, it gives. So even though I'm trying to exert the same amount of force on it as I am over here, this one's moving away from me, it's giving. So I can't hit this as hard as I can hit this. The force between us can't be the same as the force between us with me trying to do it the same. You know what I mean? Does that make sense? Not as many head nods. What are you thinking? Talk to me. Okay, the bug and the windshield. The windshield, you told me, could handle more force. The bug couldn't. So it died before it could exert more. It gave. Yeah, now what if somebody tossed a brick and you're driving down the highway? Now your windshield could break because the brick has more inertia and resistance. It could push back harder. The interaction forces are exactly the same, but that interaction pair could be bigger with a brick than it could be for a bug. So again, I can hit that. But the force on that, and likewise the force on my hand, is not as much as when I hit that the same way. Yes?
So, I think about is that you mean you push the ball and otherwise it's the same force, only like a different force and different.
I'm trying to. So I'm trying to do the same thing here and here. So if I had an identical ball over here, I'd be hitting it with the same force. But because I'm hitting two different things with different masses, different structures, there's greater force here. Was it 20 minutes already? I was going to do it next. than the rag. So I'm trying to, but the force isn't the same. I'll do this demo real fast. I'm going to put some alcohol in this rocket. There's a hole in the lid. Alcohol isn't flammable, but the vapor is. So I'm going to coat the inside of it to get it into vapor, and then I'll ignite it. The gas will light. It'll increase the pressure and the temperature inside. Where will that alcohol vapor go? Out the hole. Are you ready? Yeah. That was it. I'll have to wait a moment. So if the rocket pushes the gas out the hole, what does the gas do? Pushes back at the rocket. Which is going faster? The gas or the rocket? The gas, because it has less mass. So it's getting shot out fast for the same force. The rocket can't go as fast. It has more mass. That was it. There, now you saw it. I'll let it cool down and breathe, and we could try it again later if we get to it. Let me flush it out a little. Got to get some fresh oxygen in there. So this is how rockets work in space. A lot of people think they throw stuff out the back, and because it hits a wall or it pushes against something that propels them forward. It doesn't need anything. It can do it out there in empty space. It's just throwing something behind it. Remember our air cart on the air track last time? It pushed a slug out. Just by throwing it out, it had to push a force on it. So it pushed back and propelled the cart. That's what a rocket's doing. All right, we'll try it again. Hey, let's make it a little dimmer. Maybe we can see the flame. Ooh, yeah. Even better. All right, so all forces come in pairs, equal and opposite. Even this one, pair, equal and opposite. Not all pairs are the same, but there's always a pair. And they're always on opposite bodies. Me on the ball on me. The rocket on the gas back on the rocket. No. How many of you have ever blown up a balloon and before you could get it tied, it opens up? What's it do? Same idea. If it's pushing the air out the hole, then the air is pushing back on it. This one does the same thing. It's called a rocket balloon, but it's slightly different. Oh, I love these. They come in packs. You can get them, lots of them. So this one's weighted on the end. They tied it. And the end here is a little stiffer, so you can hear it make sound as it's blowing air past it. It's kind of like a reed in an instrument. it blows past it and the reed opens and closes to make that buzzing sound. Let's try this one. So the hardest part, I think, with rockets was how do you get it to go straight the way you want it to go? That was the aerodynamics and the fins and the control. Otherwise, it just kind of... There you go. These are toys. You can buy these yourselves cheaply. It comes with a pump, too. It's great. Rocket balloons. Here's one. Helicopters. Let's see. Blow up this one. Let the air go into here, and it redirects it through the blades. Let's see if it works today. Oh, yeah. So it comes out of the balloon through the straw, and this redirects it that way. And this one directs it that way. So it's directing it this way, and this way. Tangential. So if it shoots the air that way, which way does that air push that blade? Back. And they're all doing that. So that gets it to rotate. That gets it spinning. Why does it go up? Do you see the blades are tipped? They're angled a little bit, like an airplane wing's angle of attack. It's one way to explain them. If this is going through the air, here, we'll make it more obvious with something stiffer. If this is going through the air and it's tipped like this, which way is it pushing the air it runs into? It pushes it down. So what does the air do? It gives it an upward component. We call that lift. So as it goes through the air, there's a force up on it. If that force is greater than the weight, it will go up. It's a net force again. You need the up force to be bigger than the down force for it to have a net force up. And that's how those work. They put a reed in that one too because it's more fun when they make noise. So, unless you have a whole class of third graders doing this. I did that once. That was noisy. All right. Now, why does that rocket move at all? Some people are still confused. Why does this even move? Air pushes it. Is that the only force going on? What's the other force? Gravity is a normal force with the string. I heard somebody say it's pushing on the air. Why don't they all effectively cancel each other out? One's stronger than the other? So Newton's third law just said the forces are equal. Which one's greater? You tell me. The gas getting pushed out is greater than what? I like drawing pictures. Let's see, we'll do it. That's not too bad. All right. Well, name a force. All right, we know that. That one's down. So that's its weight. And you know how to find it, right? If we were given, that's right, mass times its acceleration down. All right, what else? Friction. Which way should I draw friction? The way it's drawn, this is trying to move that way. Friction always opposes motion or intended motion. So it's trying to slow it down. So yeah, it's trying to move that way. So yeah, friction's that way. Friction. Okay, what else? The force of the gas. Be more specific. Thrust. Who's pushing on whom? Because the gas is involved with two forces. I'm just clarifying. Okay, the gas is pushing on the bottle. Which direction? Right. Left. Right. Correct. So yeah, that's the gas on bottle. That's what's providing the thrust to make it move, right? It's trying to make it move. Is there another force? The bottle on the gas. And which way is it? Force of bottle on gas. All right, if you added all these up, which way does it look like it should be going? Down, that's right. Why doesn't it fall down? We left that one off. Yeah, the wire is supporting it. The support force or normal force is up. All right, now which way should it be going? Shouldn't be moving at all? Which forces would balance if this didn't move at all? I'll specify. Which vertical forces should balance? The up and the down, the support and the normal. Horizontally, which ones would be equal? Is it both of these and that? If it's not moving? But you guys saw it move. And it moved in that direction, correct? Does that mean this one's bigger? See the confusion yet? What you thinking, Carl? I was hoping somebody'd get there before I had to. The gas is a separate object than the bottle. So when you think about these, if you want to know how the bottle's moving, look at all the forces on the bottle only. If you want to see how the gas is moving, look at all the forces on the gas, but only the gas. Don't mix and match. So we have one problem up here. This one, it's there, but that's not on the bottle. That's not influencing how the bottle moves. Do you see that? So don't get confused by action-reaction pairs. They're always on opposite bodies. This and this are the action-reaction pairs. But this is the force on the bottle trying to make the bottle move. So now it's between these two. So the net force, horizontally, in the x direction, is the force of friction, the way I've drawn it, trying to make it go to the right, minus, remember force is a vector, it's going the other way, the force of the gas on the bottle. Is the net force 0? No, because it clearly accelerated and sped up. So that means one of these is bigger than the other, and you know which one it is. The thrust, the force of the gas on the bottle, was bigger than the friction. If it wasn't, it wouldn't have moved. It overcame friction and got it to have a net force and accelerated. So, those of you where your gut wanted to say, this had to have been bigger, don't fall into the trap that no, Newton's third law says these are still always equal. Just realize that's not trying to move the bottle. You want to know how the gas moves? Force of the bottle on the gas, Well, it's the mass of the gas times whatever acceleration it got. That could tell you how fast it accelerated, the gas, which is a different acceleration than the bottle. That'd be the mass of the bottle times the acceleration of the bottle. And this is of the gas. I just ran out of room. Questions? Yeah, so see, this is a good review of net forces, combining things, Newton's third law and Newton's second law. I think you guys all got it. Let's just put it together again. The bottle shoots the gas out. So that accelerates the gas with a given mass. Gas goes fast because it doesn't have much mass. Yes? That tells us how the gas moved. But Newton's third law says it's the exact same force that pushes back on the bottle. So now we know what this force is. It's the same as that force. But this one tells us how the bottle moves. So it would accelerate with all of that force if there weren't any friction trying to slow it down. This is a little smaller, so it clearly accelerated a lot. The net force, you got to look at all the forces in that direction. The thrust trying to make it go to our left, and friction to the right. So you add them up. Since they're in opposite direction, one better be positive and one better be negative. It's the difference between them that's going to tell you how the net force. And that net force determines how that mass of the bottle will accelerate. Since the mass of the bottle is a lot bigger than the mass of the gas, it will accelerate a lot less. I like representing that like mass of gas, acceleration of gas, mass of bottle, acceleration of bottle. How do you feel now? All right. So next time you see a collision or you're in a collision, hopefully not in a car accident thing, but you run into something, you push something, you hit something with your fist, things bump into each other. They might be different sizes like we had on the carts, so they'll be accelerated differently, but the force is the same. Now I should specify, some people get confused. This seems opposite than gravity making things drop, right? All things fall together without air resistance. What's the same there? Bless you. Acceleration, not the force. In way of review, that case is the acceleration, due to gravity, is the same for all objects. So if you have a big object and a little object, who's going to feel more force? And this is where the confusion is, because we just harped in Newton's third law. The forces are the same, right? The forces are the same for what? In general, the forces are the same for action-reaction pairs, which are always on opposite bodies. I push on you, you push on me. This isn't an action-reaction pair. The Earth is pulling on something big, or the Earth is pulling on something small. Yeah, what's the reaction of the Earth pulling on something big? The something big pulling back on the Earth. But see, that influences how the Earth moves, not the ball, or the big. When it pulls on something little, the something little pulls back. Those are the action-reaction pairs. This pair is equal. This pair is equal. But these two pairs aren't necessarily equal. Because, I'll leave it at that. But we said each of these masses will be accelerated the same due to gravity. So the Earth is pulling on which one with more force to make that happen? Very good. This one. That one has to have a bigger F to compensate the bigger inertia than this one. The smaller object weighs less. So we could do this. Here's our two masses. But you know they're going to hit the ground at the same time. Yep, sure enough. So the Earth is pulling on this with more force than it is on this. So in this case, the accelerations are the same. With in the rocket case, it was that action-reaction force that was the same. And people get mixed up. So I'm trying to just clarify. Does it make sense right now? So you can use these two laws. This is Newton's second law, incorporating Newton's first law with inertia and things. And this is Newton's third law. They're both tools now in your toolbox to help you figure out forces on things. And then once you know forces, you can determine how they'll accelerate. Like here and here. In this case, they didn't accelerate the same. The gases went faster. But in this case, we knew the acceleration was the same. So we can use that to determine that, yes, there's more force here than there is there. Okie doke. Okay, here's a question for you then. Does a moving ball possess force? What do you think? Does a moving ball possess force? Well, you got a 50-50 chance, yes or no. What do you think? Yes, yes, yes. I haven't heard a no yet. Okay. The yeses have it at the moment. Oh, here's a depends.
Feels like just like moving in space at like dynamic equilibrium.
Okay, if we're in dynamic equilibrium, what does that tell us? That the forces are equal on it, so the net force would be 0. The acceleration would then be, the net acceleration, 0. Its velocity would remain constant. So if something's in dynamic equilibrium, but it's moving at a constant velocity, does it possess force?
There's still force,
So
even if they're equal and balancing each other out, there's still force, though, right?
Yeah, if something's moving, does there have to be a force on it? Let's just pause. If something's moving, does there have to be a force on it? Give me an example of a no. What do you think? I bet all of you know one. Maybe you just don't realize it. It was actually in your homework, partially. It had to do with, if the acceleration was 0, could it still be moving? If that gives you a clue. So what's an example of something that could be moving without any force acting on it? Say that again? Yeah. Set the other force equal to 0? Yes, if the net force is 0, it definitely it'll stay moving at that constant speed. Very good. All right. Could we remove those two forces? What would happen to its speed? Let's say we push on something and we accelerate it up to a certain speed. And maybe there's air resistance, So they're balanced, and the thing's going at 50 miles an hour. And they're acting. What if we simultaneously remove both forces? Like a spaceship. There, you could, that gets rid of air resistance and turn off the thrusters, right? At the same time, what would the spaceship keep doing? It would keep moving at the exact same speed. It wouldn't automatically stop because nothing made it stop. That's Newton's first law. Things in motion want to stay in motion. So we say matter possesses this property called inertia, this resistance to wanting to change its motion. What's it take to change something's motion? Another force. So if you don't apply a force, what does the object keep doing? It maintains that state of motion. Whether it's at rest, it'll stay at rest. If it's already in motion, it'll stay in motion at that speed. Velocity, even. Thus, you can have something moving without any forces on it. Somebody over here said, I think it was you need a force to get something to move, but once it's moving, you can remove all the forces. Remember, that's my bucket list out in space. Just chuck the ball. And if nothing acts on it after that, it'll just keep going. So, back to my roundabout question. Can an object possess force? No. Never, ever. Don't think of objects as possessing force. That's my point. Force makes them change their motion, but it's not a property they possess. A force is an interaction. You've got to have an interaction to make that change in motion. And all interactions come in pairs. So if you push on something, it's going to push back. You can't push on something without interacting with it. Questions? All right, then I got one more thing, and it's the weekend. The end of this chapter brings up vectors again. So here's an example. There's a wall. Let's say you're hanging from it. Whee! Okay. The forces are going in different directions here. It's easy when they line up horizontally and vertically. We can add these up and get a net force. We can add these up and get a net force. But how do you add this to this? The bottom line, you don't. So you break them all up into horizontal and vertical. So in this case, if we looked at the forces right here, right at the ring, this actual force is pulling that way, right? And this string is pulling it that way. Now I'm going to pause. Which one of these forces do you think should be bigger? As drawn. Which side do you think is holding up the person more? I've heard more right votes than left. So let's go with that and see if it works out here. So I'm just going to draw that one a little bigger. I'll get to the punchline there. It's the right side. Think of it this way. If you hung directly under this one, and you put a little scale there, what would the scale read if you were straight underneath it? Right. Whatever force is being pulled down, your weight. What if you're directly under this one? This one would have all your weight, and this one wouldn't be holding you up at all. So it shifts that way from one extreme to another. So if you're more over here, this one has to hold you up more than that one. So I just thought I'd draw it appropriately. And then there's a force down right here, which is your weight. And it's straight down. Now they're often in two dimensions. This is all you do. We call it breaking it into components. you drop a perpendicular line to the axis. So like from this one, what part of this force is directed upwards? Well, if you do this, that is. See how it's smaller than that one? That much of it is helping lift you, hold you up. This part of it is trying to move you to the left. That's not helping hold you up. But that part is. And then you do the same thing with this rope over on the right. Drop a perpendicular to the axis, and that's the component of this force that's helping hold you up. You can do the same thing over here, and that's the component that's trying to move you to the right. Are you with me so far? Right, now you add them up like we've always been doing. You just do it 2 times. You do the x's, the horizontal, and you do the vertical. I didn't draw this perfectly to scale, but what? Yeah, you would. I would like add up the forces. You know, I want to know the net force in the x direction. Then, you know, let's say this is force 1 and this is force 2. You know, number 1, number 2. Then this is the force of 1 in the x direction, and this is the force of 2 in the x direction. So you would just add those up. They're in opposite directions, so one of them is negative. By convention, we usually say things to the right are positive and things to the left are negative. If you're not moving here, what is this net force? 0. So how do these two compare? Yeah, they'd be the same. You'd be getting pulled the same horizontally here as you did there. So these should be drawn the same length, but I wasn't exactly to scale here. If you're not moving up and down either. What's the net force vertically? Let's do the net force in the y direction. That would be 1 in the y plus 2 in the y plus your weight. That one's down. We'll say that's the negative. So those are up and weight is down. All these better add up to 0, right, if you're not moving. For completeness, this one's F1 in the y direction, and this one is F2 in the y direction. So these two equal together this one. So this should be the same length as the sum of these two. Let's see how close I got. Not too bad. I tried to. But again, you're just balancing forces. So when you split things up like that, we call it breaking things into components. We're going to do this more with projectile motion in Chapter 10, so we get to use this again. But if you have right triangles, let's say this is a force. And let's say that force is 5 newtons. This is a right triangle. Then there's a component in the x direction and a component in the y direction. If you remember anything from geometry or trigonometry, we could figure this out. This is 3 newtons, and this ends up being 4 newtons. The components will always be smaller than that. Or if you remember Pythagorean theorem, 3 squared plus 4 squared has to equal the hypotenuse squared. So the square of this plus the square of that has to equal that. I'm not asking you to do that. I just want you to realize the components are smaller when you break them up, because only part of it's directed in the x and part of it's directed in the y. If you're confused, reread that section at the end of Chapter 5, and maybe it'll make more sense now. I just wanted to give you that before the weekend. Have a good one.
Thank you.